Well, I solve a Leetcode problem like every other day. This is 2934 2934 minimum operations to maximize last elements in array. Look at this. You see this? People always ask me, dude, you're so muscular for a nerd. You know, they say, dang, dude, where you get them guns? And the reality is, when you're working on Leetcode problems, it takes such a tremendous amount of focus that you actually become strained, and so strained that you develop a muscular form as a result. So gym membership's not worth it. I'd recommend Leetcode. That's how you get totally shredded. Okay, you're given two zero-indexed integer arrays, nums1 and nums2, both having length n. So, we're given this example. You're given nums1, nums2. They have the same length n. Okay. You're allowed to perform a series of operations, possibly none. In an operation, you can select an index I in the range 0 to n-1 and swap the values of nums1 and nums2 of I. So that means you can vertically swap values within the array. So we're going to do example 2, so might as well just draw that out so you can understand better what it means by vertically swapping an element. Right? There's always the very mathematical way of describing what a problem is stating, and there's also kind of the visual way, which is usually far easier for us normal people, us plebs, to understand. Okay, so we have nums1 equaling 2, 3, 4, 5, 9. Can you guys see that? And we have nums2. Nums2, what's it do? Nums2 equaling 8, 8, 4, 4, 4. Now, what it means by swapping at I, that means you can swap at the same vertical index, right? So if I draw a vertical line here, I can swap this 3 and this 8, resulting in, well, more or less the same array, but with these two elements, you guessed it, swapped. So the 8 goes over here and the 3 goes over there. Right, so there's just vertical swaps. Notice there's no horizontal swaps, right? In any place I can do one thing, right? I can swap this with a 4, swap this 4 with a 9. That's it. This 5 with this 4 is 4 with this 5. This 4 is 4 is 4 with 4. But I can't swap, this 8 with this 9, and that point will become important in a moment. Okay. Swap the values. Your task is to find the minimum number of operations required to satisfy the following conditions. Nums1 of I, n-1, so this is the last element, right? So nums of I, n-1, that's the last element, right? Because the length n, so then the last element would be at index n-1. So this would be nums, just so you understand what's going on here, this would be nums1 of n-1, right? This element here. Right? This nums of 1, n-1, needs to be the maximum value among all the elements nums of I, i.e. nums of I is the maximum of all of these things. So what does that mean? It just means that's the largest element in the array. It doesn't have to be the unique largest, right? It just has to be the largest one, right? So, imagine there was multiple 9s. It just has to be equal to the largest thing, right? It doesn't have to be taller than everything else, but it has to be as tall as the tallest thing, right? So it has to be 9. If this is the largest element, then there could be other 9s, but everything else has to be less than or equal to 9. Hopefully that makes sense what I'm saying. It'll make sense in this example because we'll end up having 4 be the maximum, even though there's multiple 4s. And the same thing for nums2, right? So the last element nums2 needs to be the maximum value nums2. Okay, so we're going to return an integer denoting the minimum number of operations needed to meet both conditions, or -1. If it is impossible to satisfy both conditions, return -1. Okay, so this is one of those problems where you look at it initially and it can be kind of overwhelming because you're like, okay, I can make swaps as I go through, but then depending on like how I swap, wouldn't that affect what the maximum would be? So then now that I'm affecting what the maximum would be, do I have to look back and then change the things that swapped before? It's a little complicated. Let's first do this example, and then we'll try to use some reasoning skills that can really help us kind of, take this problem and just smack it across it. Just, come on. This problem's simple. You know what I mean? It's really easy if you just try to compartmentalize the information and use that to determine how simple this problem can truly be. Okay, so in example 2, we have nums1 equals this, and nums2 equals this, and the answer is 2. Well, why is the answer 2? I'm going to delete this because this was just to show an example. May not be what we actually want to do. Turns out, to make this thing minimum, oh, that is actually what you want to do. You're going to swap this 3 and this 8, and you'll notice, well, 8 is the maximum nums2, but if we swap it with this 2, right, if we swap it with this 2 here, right, because we can do vertical swaps, we end up getting the following. And then you'll notice that everybody's happy in this situation, except my hands that I just hit really hard for some reason to be dramatic. And I don't know why I did that because people probably think I'm a psychopath now, but that's okay. So 2, 3, 4, 4, 4. You'll notice that 4 is the maximum thing in this array, right? It's not uniquely maximum, right? It doesn't mean that everything's less than 4, but it's as large as the maximum thing. So that meets this second condition here. And this 9 is the largest thing here, right? 9 is larger than 8, 9 is larger than 8, 9 is larger than 4, 9 is larger, 9 is largest, 4 is greater than equal to 4, greater than 4 equal to 4, of course greater than equal to 3, 4 is greater than equal to 2. Right? 9 is greater than equal to 5, 9 is greater than 4, 9 is greater than equal to 8, and 9 is greater than equal to 8. Good stuff. Okay. So that means in 2 swaps, right, we can get a situation that works, right? Now, the reason why there's a -1 is that it's possible, right? For example, here, this 5 can only swap with this 5. So this 3 is never going to be a good situation for this 3, right? This 3 is always going to be less than this 5, and less than the 5 you can swap it with. All right. So what do we have to do when we look at this problem to think about how we can simplify it and kind of programmatically, structurally, procedurally find the solution? Okay. The first thing, and kind of the only thing is, you can do a bunch of swaps, right? But in all honesty, the only thing we care about, right, and we're going to use the examples, the only thing that really matters in this problem are these 2 special guys here, right? The only thing that matters are this 9 and this 4, right? Because that's what determines if we can make this work, right? The condition is that everything in nums1 has to be less than the last element, and everything in nums1 has to be less than or equal to the last element in nums1, and everything in nums2 has to be less than or equal to the last number in nums2. Okay? So there's really only 2 things you can do in this situation, right? You can leave this alone and try to make it work, or you can swap and try to make that work. And what I mean by that is, like, those are the only 2 things you can do here, right? You can either make it look like this or look like that, right? You can either have 4 and 9 or 9 and 4, okay? Now, the reason why this is important is, well, this should really kind of minimize. Now, of course, I guess one thing to think about here is if you do this swap, you've already done one operation, right? But now what you can think about is, well, okay, these are the only 2 situations we could be in, right? Either I'm trying to make everything in nums1 less than 9, or I swap and I'm trying to make everything in nums1 less than 4. So the reason why this helps is it really contains what you're trying to solve, right? Because now it's a much simpler problem. I don't have to think about the variable anymore because there's no real variable, right? There's just 2 separate problems. There's a problem where I'm trying to make everything in nums1 less than 9 and nums2 less than 4, or I'm trying to make everything less than nums4 and nums1 and everything less than 9 and nums2. Right, so now the problem has been simplified considerably because it's easy to kind of figure out if everything can be made less than 9 or 4 in nums1 and nums2, and if everything can be less than 4 or 9 in nums1, nums2 in this situation, right? And in order to do that, all you have to do is look at the 2 and the 8 and decide if you swap. And if you swap, will it still be okay, right? So here when I'm looking at this, I say, 2 is less than 9, that's good, but 8 is not less than 4. So what I'll do is I'll say, well, what if I swap? Well, if I swap the 2 and 8, I get 8 and 2. 8 is less than 9, 2 is less than 4. So that's good. So that means in order to make this work, I need to swap the 2 and the 8 and add 1 to my score. And then you just move on to the next element. 3 is less. And you look at 3 and 8, right? Because the thing here to remember, right, is that you can only vertically swap. So there's only two things that I can really do, right? I can leave them the same, or I can swap them. And since I've already trapped these values, there's no variance, right? I just look at this problem individually and say, is it less than or equal? Is less than or equal to is less than or equal? Right here I say, okay, 3 is less than 9. 3 is less than 9, but 8 is not less than 4. So what am I going to do? I'm going to try to swap. If I swap, does it work? Yes. 3 is less than 4. 8 is less than 9. So that's going to add another 1 to my score. I say, is 4 less than 9 and 4 is less than 4? Yes. 4 is less than 4. 4 is less than 9. Say, is 5 less than 9? 4 less than 4? Yes. 5 is less than 9. 4 is less than 4. And just to keep this consistent, we'll keep it like this. So every time I cross, I have to add another point, right? Every time I have to swap to make it work, I add another point. But every time I leave it the same, I don't have to, right? Now, in this situation, I've already got a point because I've already had to make a swap, right? Now, I look at 2 and 4. I say, okay, is 2 less than 4? Is 8 less than 9? Yes, we're good. Let's just continue. All right, 3 and 8. Is 3 less than 4 and 8 less than 9? Yes, we're good. Let's continue. 4 and 4. Is 4 less than 4 and 4 less than 9? Yes, we're good. Let's continue. 5 less than 4, 4 less than 5? No. I have to swap these to get 4 and 5. Add that to my score, and I also get 2. All right, so in this example, you can do one or the other, and you get the same result. All right, and then let's quickly, so I think you see the flow of this, right? You go through each vertical pair for each situation, and you say, okay, does this work? Does this work? Does this work? Let's look at an example where it never works, so you can kind of see why there's a -1 case here, right? So let's say we have nums1 equaling 154. And then we have nums2 equaling 253, okay? Now again, we don't like this idea that 4 and 3 could be either way, so let's just split these into two problems, right? So we'll keep it the original problem, 154, 253, and then we'll have the new problem, 153, 254, all right? So now we just have these two contained problems where we can just run through and play this game, right? So here we say, okay, 1 less than 4. Now, of course, I keep forgetting, right? Our score is already 1 here. And our score is 0 here to begin with because we didn't have to make a swap, right? We're assuming we did a swap here in this situation, so we already have to add 1 to our score. Okay, 1 less than 4, 2 less than 3. Yes, we're good. Okay, here's where it becomes an issue, right? Because 5 is not less than 4 and 5 is not less than 3. But if I swap them, 5 is not less than 4, 5 is not less than 3, right? And here's really showing this kind of vertical swap, what you're actually able to do. It really, simplifies the problem, but it also limits what you can do when you're in these kind of situations, right? Because there's only two things I can do. I can leave them the same. Doesn't work. I can swap them. It doesn't work. Doesn't work in either situation, so we're kind of screwed in this case. What if we swap them? Does that do anything for us? It really doesn't, because if one doesn't work, the other one doesn't work, right? Because you're trying to swap. So if you've already swapped the other side, it doesn't really matter. But just to show you, 1, 2, that looks good. We look at 5, 5. Can we swap 5, 5? No, right? We swap it, doesn't change anything, right? Even if it's not 5, 5, if they're different numbers, right? Sometimes when you swap them, it's not going to help, right? If you had 7 and 5, for example, because I don't want people to get strung up on the fact that it's 5, 5, right? If you had 7 and 5 and this was 2 and 3, right at the end, you swap 7 and 5, it's still greater than 2 or 3. So there's nothing you can do there, right? But in both these cases, there's nothing you can do. So you would return -1. All right. So with that said, let's code it up. Now I'm going to be completely honest with you guys. I am not going to write the cleanest code today. I'm just going to write something that gets us to the end. So we're going to kind of speed code this, right? So if we do no swap, our score is 0 at the beginning. If we assume a swap, our score is 1 at the beginning, okay? Now, we've already made a swap on the last element, so we don't need to look at the last element. So at the end, we would return the minimum of no swap and swapping, right, of course. And then let's look at each element in the range length of nums1 -1. And that's because we don't need to look at the last element because we've already swapped it, right? So now we play this game. We say, okay, if the current element we're looking at in nums1, if we have an issue, what does it mean if we have an issue? Where the current number we're looking at in nums1 is greater than the last element in nums1. Because what that basically means is we have an element where this is greater than what we want to be the max, which is the last element, so we're going to have to do a swap. So we can do that in nums1 case, or we can do it in nums2 case. Okay? So if it happens in either of those cases, we have to swap. So if we do a swap, we're going to add 1 to our score. Okay? Now, if we make the swap and it still doesn't work, what does it mean for there to be a swap and it still doesn't work? If nums1 of I is not less than or equal to nums2 of -1. Because what happens now is we're swapping, right? So before we were thinking about, we want nums1 of I to be, if it's the case where num1 of I is greater than nums1 -1, we're in an issue. So now we're going to try to swap them. So now what used to be nums1 of I would be nums2 of I. So we compare that to nums2 of -1. So if that's the case, so if it's still the case that it's an issue, right? If nums1 of I is greater than nums2 of I, or nums2 of I is greater than nums1 of -1, we return -1. Because basically, we've hit a wall, right? We've swapped, and we swapped again, and it still doesn't work in the end. So if we swap the ends or didn't swap the ends, it doesn't really matter. But if we swap and it doesn't work, then there's nothing we can do. We've hit a brick wall because we can't vertically swap here, and we've already swapped at the end or didn't swap at the end, but either way, right? There's no orientation of these 4 numbers where it works, right? So we return -1 if that's the case. And then we kind of play the opposite game if we've already made the swap, right? Because if we've already made the swap, we're assuming that what was in nums1 of I, the last element, those have been swapped with each other. All right, so now we can just, now nums1 of I is going to be compared to nums2 of -1 because we've made that swap. And was nums2 of I is going to be compared to -1, nums of 1. So then since we swapped them, they're actually together now. Yeah, and then this is non-swap. And we'll try that. Ooh. Okay, let's see. Oh, I got this backwards, right? Because this is non-swap should be 1. Wait. This is not, okay, this is the non-swap case here. We didn't swap here, so we add that here. This is the swap case here. Apologize. Because this is the case where we swap. That's why we already assume that nums1 of I is going to be compared to the last element. All right, cool. So what is the runtime and space complexity of this problem? Well, they're the same length, right? It's that nums a length n. All right, let's do space first because it's much easier. All right, all we do is we create these 2 variables and then we update them accordingly within the loop. That's it. All right, we never create additional things that are, if there's a million elements or 4 elements, we only create these 2 variables and update them within the loop. So that's constant space. For time, well, we have to look at all elements. So we look at all n elements, right? N minus 1, I guess. And we do a constant comparison. We add 1 to this variable's value. We do another constant comparison, constant. We do like 4, 5, 6, something. 6, 4, 5, 6 constant operations, right? So that's 6n or just n. 6n minus 1, I guess. So 6n minus 6, something like that. But that's proportional to O of n. Okay. All right, everybody. Have a good rest of your day.